Hey, good morning. How is everybody? Peach cinnamon rolls. That sounds good. Yeah, I had a late night. I'm debugging circuits, so I could use a nap. Um, oh, somebody wants a PA6. Excellent. PA6 will be in spring quarter. Yeah, it's always fun. I used to do my classes from my desk right in front of my window. And one of the reasons I stopped that was because the recycling truck or the garbage truck or the lawn care people or the delivery people or something would always come and like idle right underneath the window. So, and in springtime, the windows are always wide open, so it gets louder there. Um, PA6 as an ODP that replaces our final. Well, that sounds like an interesting trade. Someday I will figure out how to do programming finals where, people basically do a bunch of ODPs and that's your final exam. I would love to do that. I think it's a much better assessment than writing code on paper. Um, but I don't have a handle on how to do the logistics of that yet. But someday. All right. Well, let's talk about the SLPs. So, I thought that the presentations that I saw and the projects and the attendance and the enthusiasm and energy level, I thought those are all fantastic. I was really happy with the turnout. I think I only had two unexpected no-shows, and we did have a number of people come in to visit from outside, mostly people outside Clark, some who work with small startups and things like that. Came around and listened to people's presentations and asked about their projects and things like that. And so I think that was really cool. So thank you everybody for participating in that and putting up with the kind of quirks about getting into rooms initially and things like that. If you have any comments, feedback, discussion, or anything like that, let's just talk about this for a few minutes if you like. And I'd love to hear any reactions or feedback from people on the presentation, the format of it, the mechanics, and so on. Any reactions or thoughts? Or not? All right. Yeah, there was confusion about that, so I tried to make it clear earlier that you were presenting during your class time. So section A, 10 o'clock to 10:50. Section B, 11 o'clock to 11:50. But a lot of people showed up at 10 and thought they had to stick around until 12. So hopefully that got cleared up and people didn't um, stick around extra. Um, Izad was asking his students to stay till 12 because he has a 2-hour class. Um, but there was a lot of crosstalk going on. 6 times, wow, awesome. So you're probably really good at presenting. Um, and so I wanted people to be there for the 50 minutes. Um, and if there was, only one person in your room, then you probably ended up talking a lot. If there was a couple, then you might have presented, 4 times or more. Um, and that's okay. The more you talk about something, the more you start to understand it actually. And if you're working on something that you plan to take further or might want to take further down the road, I think the presentations can be a good opportunity to sort of refine the ideas. Um, and sometimes it's just fun talking about something you've been doing. Let's see, 6 times, 4 times, cool. There was also some confusion up front about how to get into a room, and I think we're going to try to post some instructions next time that show like where to find the breakout rooms button and so on. Because in my 222 class, 224, we don't really do breakout rooms. My 101 class, we do breakout rooms every week, so they're experts in doing breakout rooms. But I think we need some instruction on that for students and for visitors, because a lot of people weren't able to put themselves into rooms. Yeah, and the breakout rooms are kind of fun. There's a lot you can do with them, but it's like a lot of Zoom. Some of it's kind of hidden. We also need to figure out, because Izad was hosting and I was co-hosting, and it didn't seem to let me as a co-host move people into rooms. So there's details to work out. But this was our first attempt at this, and so thanks for being guinea pigs. Definitely neat seeing what other people are working on. And one of the nice things when this is done in person is, everybody's in one room, and you can just kind of scan the room and see, if somebody has something sitting on their table or something like that. And the in-person SLP is usually 2 hours, and so there's time to kind of walk around and visit other people's tables and see what they're doing and so on. And that's definitely a cool aspect. Yeah, that's a little awkward, right? If you're presenting and all of a sudden the one person in the room leaves, do you keep talking to an empty room, or do you stop at that point? Um, and it always feels a little weird to me to like be talking when nobody's listening. Um, but you can if you think they got kicked out, you can wait a minute to see if they come back, or you can just continue talking and just play town crier, or just speak your business to the world for the universe to hear. But yeah, it is a different experience in person. The universe is always listening. I think that's true. That's a good point. Oh, cool. Nice, nice. Yeah, you'll be surprised what you end up talking about sometimes. Um, yeah, so presentation skills can be good. Oh, awesome! Thank you. All right. Well, good work on the SLP. I'm pretty sure that. Oh, nice. um, I'm pretty sure that spring quarter will still be online, but I think we'll have a few more details worked out for the online version, and like I say, typically more people from outside coming to see that. So hopefully we'll have a setup where people can more easily see what the projects are, and maybe have a place they can preview the posters or something, and and that should be a good setup. All right. So if you have any other feedback or anything like that, feel free to send me email or talk to me in office if you got other things you want to say or ask about SLPs. So what about PA5? Hopefully everybody turned in PA5. I've got like 38 submissions, which is pretty good. 4 in the morning, yes. I'm pretty sure you are not alone. Yeah, and quite unfortunate timing-wise, GitLab went down for a bit. It was either down or really slow. I was able to get to their website, but trying to push code was timing out. And I don't know how long it was down. I heard about it, and about an hour later, it seemed to be back up. And that would be a real bummer if you know, it was down all night. We would figure out something to do, like I'd have you submit on Canvas or something like that. But it made it back up, so that's good. Git's usually pretty reliable. GitLab, GitHub, they occasionally have issues, but they usually get things together quickly. Yeah, I was surprised too. Get things together, awesome. Yeah, Xbox and Sony. So I'll start grading PA5 today. It may take a few days because normally I have a weekend. Um, but I'll start grading it today, and I usually post all the grades simultaneously. So it might be a few days till you see those. But generally, it seemed like people were being pretty successful getting the maximum value to work, and then mostly running into issues with the item count, and then to a maybe lesser degree running into problems with the caching. Um, and we'll talk about those after I've looked at people's code. But any urgent questions on PA5 that you want to go over right now? Initializing the structs. And this is an assignment where lots of little things can get you, like not initializing max vals to 0 in a cache, or you know, having a star when you shouldn't, or not having a star when you should, or declaring your array to be size n and then looping from 0 to n, which steps on memory. And lots of little things like that. Ah, array indexing seg faults, there you go. And you know, one trick that I used to do when I would get things like that, I would just make my arrays really big. If I know that I need, you know, around 128, I'd make my array like 2000, just to try to eliminate that variable. And if that fixed my problem, then I'd start looking around that. Now you can use GDB or Valgrind and be more nuanced than that. But a big part of debugging is getting good at making bugs appear. And so you've heard me talk about trying to find a minimal case, right? And it doesn't have to be the minimal case, but if your program is seg faulting with a capacity of 20, that's going to be a lot of GDB stepping, potentially, to get to the seg fault, especially if the seg fault happens after your max val function is done. So go in and change the inventory file and change the capacity. Try to break it with a simple case, right? And then if oh yay, someone made friends with GDB and Valgrind, that's awesome. if you can get your program to break, with a capacity of 3, then you're not going to have to do as much recursion, as many calls, as much stepping in the debugger to get to where the error is happening. So trying to find, kind of a minimal test case. To some degree, you can use test cases to try to understand the problem. That's hit and miss, though, right? So you can maybe narrow it down to, oh, if my recursion goes more than 2 levels deep, it blows up, right? But that works, if you really understand your code well, like if it's something you've been working with for a month, and now you've made some change and something's going wrong, you may be able to kind of reverse engineer from the types of situations that cause the errors. You may be able to reverse engineer from that to where the problem is in the code. But that's its own set of challenges. But yeah, trying to find a way to make bugs occur is a useful part of debugging. Kind of a homeopathic approach. So the reason I said not to worry about Valgrind too much is because, yeah, if you're not allocating memory, you probably won't have any memory leaks. If you don't close your file that you use to read the database, you'll get a memory leak report from Valgrind, but I'm not worried about that. On the other hand, I did suggest using Valgrind to find things like uninitialized variables, because that will definitely help. Hey, no worries, better late than never. So Valgrind, yeah, will definitely be your friend. And just always do it when you've compiled with a -G, because you get extra help sometimes. You can do a Valgrind -V, you get more info, but sometimes that's too much info, because even if your program runs perfectly, that spews out a bunch of information, and it can be hard to know if there's an error in the middle. So I like just straight, Valgrind program name, and then arguments. And remember, if you're using GDB, and you want to use arguments, like say you've got knapsack 10 data.text. If you want to GDB it, compile with your G switch, and then do GDB knapsack. And any arguments you list here, those are arguments for GDB, right? So inside GDB, when you say run, you say run 10 data.text. So that was in that note, that announcement I made yesterday. Yeah, well, it's Funny D Tuesday. Exactly. Run and start are slightly different. You could say run or you could say start, I believe also works. I think start goes ahead and puts a breakpoint at main, and I think run maybe doesn't. But if you say break main before you do this, then run should work fine. But I think you can do this with either. I haven't actually tried. I think I just always do run when I'm putting arguments on. All right, well, let's talk about AVL trees. So, we talked about binary trees, and PA4 was all about binary search trees. And an AVL tree is still a binary search tree. So it's binary, right? Every node has 0, 1, or 2 children, and it has this property that, everything to the left of a node is smaller, everything to the right of a node is larger. An AVL tree, and these are people's initials, and I can't pronounce their names correctly, I'm pretty sure. But that's the three people who came up with this algorithm we're going to talk about. An AVL tree is a balanced tree. And remember the basic game plan with binary trees. If they're nice and full and fluffy, right, I can double the amount of stuff in this tree by just adding one more layer down here at the bottom. Right, so this tree has 15 nodes. I can add another 16 nodes by just going one layer deeper. And most of our algorithms, traversal, search, insert, delete, most of these, start at the root and work their way down to a leaf node. And so if we add one more layer, then the length of that journey, that traversal from the root to a leaf, increases by 1. Right? So you can double the number of nodes and you only have to do one extra operation. And so this is where this underlying log n characteristic comes from. And it's because increasing levels, exponential growth in the number of pieces of data you have stored. But this only works if your tree is nice and full and fluffy. Right? So I could have 31 nodes in here and have to go down a total of, 1, 2, 3, 4 hops. Or, we could have the highly pathological tree where we have 31 nodes in one big long line. And here, I might have to go 30 hops to get from the root to that leaf node. And if I were to add another 32 nodes to this and they ended up, in this same linear structure, I would double the amount of time that it takes to search for something. Right? And so this looks more like an order n. So the punchline of all that is we like our trees to be nice and full and fluffy. We like things to be filled up at a higher level before we move down to a lower level when we're storing, for example. And with what we've done so far, we have no control over that. If you receive data that looks like this, right, we're going to put the 40 at the root, the 20 is going to have to go to the left, the 50 is going to have to go to the right. We've got a balanced tree. But if your data had come in this order, we would have started with a 20, the 40 would go to the right, the 50 would go to the right, and we have an unbalanced tree. So with what we have so far, our algorithms for insertion, deletion, and so on, the balance of the tree is kind of, based on the data. We have no real control over it. An AVL tree is always balanced, and the trick to keeping a tree balanced is whenever you add or remove something from it, you adjust it. So if your tree begins life balanced, and if your tree starts off as null, a null tree is balanced, so it does begin life balanced. And if every time you add or remove it remains balanced, then your tree will always be balanced. So the question is, when we add something, what can happen to unbalance our tree and how do we fix that? Or when we delete something, what could happen to unbalance our tree and how do we fix that? And so we're mostly going to look at insertion, but deletion really works the same. But let's look at inserting into a balanced tree. So this is balanced, right? It's not, completely full and fluffy, but looking at the root, this subtree has a height of 1, this subtree has a height of 0, so the heights are similar. We know that the tree consisting of one node is balanced. And this tree right here, 10, 5, while the left subtree has a height of 0, the right subtree is null, so it's a height of -1. So the heights are similar, and this is balanced, and this is balanced. So 10, 5 is balanced, and so this whole tree is balanced also. And it's not, perfectly the same. It's not symmetric left and right, but it can't be, right? This 5 has got to go somewhere, and wherever we put it, there's going to be some asymmetry. So we can't just look at it and say it's lopsided. You have to apply this question of balance. So the first thing we want is to define something called a balance factor. And a balance factor is a number that we put on each node that measures how well the tree is balanced from that point downward. Alright, so the balance factor is a measure of how well the tree is balanced from a particular node on down. And we find the balance factor by taking the height of left subtree and subtracting the height of the right subtree. So we're talking about the balance factor at a particular node. And the only way you find it, find the height of the left subtree, find the height of the right subtree, subtract. You don't use the balance factor to find balance factors. This is the height of the subtrees, not the balance factor of the subtrees. So let's look at the 5. Okay, let's just pretend that 5 is the root of a tree. What does its left and right subtree look like? So what are the left and right subtrees of 5? It's not a trick. It's just a random question. Null and null, exactly, right? So leaf nodes, they have no children, so their children are technically null. So the left and right subtrees are both null. The height of a null tree is -1. So -1 minus -1 is 0. There's no difference in the height of the left and the right subtree. So this node has a balance factor of 0. Okay, basically means that the left and right subtrees are exactly the same height as each other. Okay, so the 10 node, the right subtree is null. The left subtree is just a single node, 5. So what's the height of a tree containing a single node? Zero. Perfect. Good. So the left subtree has a height of 0. The right subtree has a height of -1. So the balance factor equals 0 minus -1. And that's equal to 1. Okay, here's another leaf node with no children, so the balance factor here is definitely going to be 0. Now for the trickier one, what's the balance factor of the 20? So the left subtree looks like this. What's the height of this tree? That's a height of 1. Good. And the right subtree looks like this. It's a 40. And we saw the height of that is going to be 0. So the balance factor of this node is 1 minus 0, which is 1. Alright, so as we're working with AVL trees, we're going to be continually looking at balance factors. And in this case, the balance at each node is 0, 1, 1, and 0. Alright, so it turns out a tree is balanced if and only if each node has a balance factor of 0, positive 1, or negative 1. And so this is another way to see that this tree is balanced. All of the balance factors are 0 or plus or minus 1. Yeah. The flip side of this is if any node has a balance factor whose absolute value is bigger than or equal to 2, then the tree is unbalanced. Alright, so if we start with a balanced tree, meaning all these balance factors are, 0 plus or minus 1, and we do an insertion, so we insert something at a root, at a leaf node. So we tack something here or down here or on one of these. What we're going to do is we're going to adjust the balance factors based on that insertion. And then, looking at those balance factors, we'll know whether or not the tree is balanced still. And if it's not, we're going to want to do something to change the shape of the tree to make it balanced again. Alright, so basic game plan. We're going to have balance factors on our nodes. When we add a new node, we're going to look at the new balance factors, and if we find a spot where the tree is unbalanced, we're going to make an adjustment to change the shape of the tree. Now the trick is we can't just change the shape of the tree. If we, insert a 1 down here, we're going to find out that our tree is unbalanced. Well, we can't just move that 1 over here to balance things, because it still has to be a binary search tree. So let's look at that case. So here's a 20, there's a 10 and a 40, and what did I have at 5? And now we tack a 1 on here. So if we were to calculate balance factors, this would be 0, this would be 1, this would be 2. Right there we can see our tree is unbalanced. We can't just move that 1 over here or over here because it won't be a BST anymore. But we can take this, which is really our unbalanced tree, and we can change it into this. And this is beautifully balanced. It's actually completely symmetric left-right. So balance factor everywhere will be 0. It's still a BST. 1 is less than 5, 10 is bigger than 5. And if we pop this in place of this, what we're going to end up with is the following. We have 20 and 40 over here on the right, but on the left we'll have our 5, our 1, and our 10. And this will have a balance factor of 0, 0, 0, 0. This tree has a height of 1, this has a height of 0, so this has a balance factor of 1. And so this will be balanced again. So in this particular case, adding a 1 over here to the left of that leaf created this lopsided branch that we needed to change into this tree-like branch. And that process is called a rotation. And the way I kind of think of it, right, this was our lopsided branch. So here's a 1 down here, there's a 5, here's a 10 up at the end. you're basically taking this and you're just going like that. Okay, so that's the sense in which it's rotating. We're kind of pivoting around this middle number and changing this linear structure into something like that. And if we had a branch that was, you know, hanging off to the right like this, we could do a rotation where we turn it to look like that. All right, and that's the whole business of AVL trees, is understanding these rotation operations to try to take an unbalanced section of the tree and rebalance it. All right, everybody good so far? All right. So it turns out when you add something to a tree that was originally balanced, there's 4 possible situations you can find yourself in where you're unbalanced. And the first 2 to think about are what we call left-left and right-right. This was the case we were just dealing with. We had, you know, sort of things in a line over here that were lopsided on the left. And in this case, if we think of this as node 3, 4, and 5, the correction to a balanced state was, you know, move the 4 up to the root, bring the 5 down on the right. So that's that pivoting operation. And this is a symmetric case on the right side where you had a linear set like this, and you take that 3 and bring it down, bring the 4 up, and you end up with this case. But there's 2 other possibilities. Right? It could be that we added something over here. And now the balance factor at this node is a 0. The balance factor at this node, well, this tree has a height of -1, this has a height of 0. -1 minus 0, this has a balance factor of -1, which is still okay. And at this node, the left subtree has a height of 1, the right has a height of -1. So 1 minus -1 is 2. And so right now we can see our tree is unbalanced. And we can't do a simple rotation to restore this. But we can do 2 steps. What we can do is we can change this into the case that we were just looking at. We can rotate this little subsection of a tree like this and basically turn this into the following. Right, like that. So here we've taken the 5 and the 7, so here's a 5 and a 7, and we've just gone like that. So now the 7 is up here and the 5 is down here. And now we have a case where we have that same kind of imbalance we had a moment ago. And now we can take this, and we can take those 2 nodes, 5, 7, 10, and rotate them like this. And so this will turn into 20, 40, and we move the 7 up to the root, put the 5 on the left, the 10 on the right, and there's a beautiful looking fluffy tree. So in some cases we can do a single adjustment. In some cases we do a preliminary adjustment to make a different kind of imbalance, and then we do this adjustment to rotate to a balanced tree. So there's 4 types of imbalanced trees. This one we call left-right, or just LR. And it's called LR because the whole tree is lopsided to the left. There's more stuff on the left in a bad way. But in that left subtree, the real imbalance is caused by this extra stuff on the right. Whereas this one we call left-left. Right, the tree is unbalanced on the left, and if we look at that left subtree, that itself is unbalanced on the left. And there's a symmetric pair. There's a right-left and a right-right. And so here's Wikipedia's beautiful picture of these 4 cases. Right, the left-right case, you're heavy on the left and on the right in that subtree. Left-left is just heavy on the left, and then the symmetric version's on the right. And this also captures the exact mechanics for correcting these cases. So if we just look at left-left, right, we take this, so you find a spot where your balance factor is 2 or minus 2, right, and we call that node 5. And if that's the case, its left child will have a balance factor of 1 or 0. That's how we identify a left case versus a left-right, where the left child of that imbalanced node has a balance factor of minus 1. So look at your imbalanced node, check the left child. If it has a factor of 1 or 0, you're in a left-left case. And now we just sort of label these nodes. This is node 5, node 4, node 3, and these subtrees are labeled A, B, C, and D. And the correction to this tree is to basically turn it into that tree. So move 4 up to be the root. 5 becomes the right child of 4. 5's right child remains D. But now 5 is space on its left side, and 4 lost its right child C, so 5 is going to adopt that on its left. So 5 is rotating down, and C is coming up to be the left child of 5. And then 3 just stays left child of 4. A and B stay the left and right children of 3. So these things don't change. That's still the left child of 4. The only thing that changes is node 5 comes down to the right of 4, and C gets picked up by 5. But let's see what this does to the sort order, because we want a BST. So if we traverse this tree in left node right, so an in-order traversal of this tree right here, right, we're going to basically move as far to the left as possible, which will bring us down to a complete traversal of subtree A, followed by printing out the value of root node 3, and then a complete traversal of subtree B. And that completes the left subtree of node 4, right? So we just traversed this left subtree, got A3B. Now we print the root node 4, and then we traverse the right subtree, which is C. And that is the complete traversal of the left subtree of 5. In other words, all of this stuff. So after printing all of these, we're going to print the root node 5, and then we'll traverse the right subtree D. So before we rotate out of the left-left case, this is the order in which we would expect to traverse our nodes. Make that a little brighter. And once we apply this rotation and our tree looks like this, what's the traversal order? Well, we're going to move to the left. We're going to traverse this left subtree. So again, it's going to be A3B. And then we're going to visit the root node 4. And then we're going to traverse the right subtree, which is C5D. And you can see you get exactly the same order of nodes. And as long as this was a binary search tree to begin with, doing this left-left rotation does not disturb the order of the nodes in your traversal, so it's still a binary search tree. It's a little harder to show that this ends up being balanced, but you can work through that and see that this imbalance of 2 will go away, and your root node will have a balance factor of 0 or -1, and everything else will be balanced. So that's the basic idea of an AVL tree. And then for a left-right case, right, you turn this into this initially, and you can show that the traversal order of this, well, it's going to be A3, B4, C, 5D, right? It's going to be exactly the same as the traversal order of this. So it doesn't change the order of the nodes. So the next step is to actually put together some trees and go through these steps and kind of see how this works with some particular examples, and start adding things into trees and rebalancing, and see what happens. And I'm not going to start that today because we only have a minute left, but we'll start that tomorrow, and then we can look at some code for actually doing this. And coding this is challenging, right? You just went through coding a pretty large project and trying to deal with all the little details that interact with one another. Same idea with this, right? It's a straightforward algorithm, but wow, if you get one thing slightly off, you know, everything goes kind of fluey. So it's potentially tricky to code, but it's a pretty straightforward process. So we'll look at some code that implements this, and we'll play around with that. And then maybe we'll talk about red-black trees, which are another way to balance trees. Yeah, that's the story of everybody's life, trust me. It doesn't stop. It just gets a little easier to deal with these kinds of interconnected details. But yeah, that keeps happening. Yeah. All right, cool. That's all I got for today. I'll let you out 5 seconds early. Have a good afternoon. I will see you tomorrow.